Okay, now, so indirect addressing. Indirect addressing actually depends on which space you're talking about. So if it's your internal data space, then you use R0 or R1. And you're limited to R0 or R1. You cannot use R2 or R3. That's a restriction imposed by A51. Why is that? Because that's how they design the instructions. So if you have two registers to choose from, that takes just one bit. So if you look at the way they encode, anytime there's an indirect addressing like R0, R1, they really just have one bit to stick in the 0 or 1 in there. Okay, they pack everything really tightly. Um, so if you want to use a register as a pointer to your on-chip memory address space, then you must use either R0 or R1. And you might ask, why just two? Well, usually two is enough because if you use one of them as a source, one of them as a destination, then yeah, that's actually enough. Now, if you were accessing either X data or code space, then you should use DPTR. So you would load the DPTR and then do the move X or move C. Now, uh, and in fact, if you want to address the external data or external or code space, the only way to do it is through DPTR. There's no direct addressing mode for DPTR for the external code space or data space. The only way to do it is through DPTR. So direct addressing is for the iData space only. Okay, and that's one byte pointer or one byte address. So let's look at the difference between like direct addressing versus register indirect addressing. So again, these opcodes in assembly all look like move, but they are entirely different. Right? And in the top case, you can do move A 02. So the 02 is hard coded as part of your instruction. But if you do move A comma at R0 or R1 with the at, then that address is changeable, right? So you're using the register R0 or R1 as your pointer. As a pointer, it's convenient because you can calculate. You can do an offset, you can increment, you can do whichever, right? And then dereference it. So as you remember in C, you have pointers. Well, here this is your pointer, except the pointer is now in register, okay? And it has to be R0 or R1. Now, being able to compute this pointer is convenient. You can do array access, or you can do some kind of struct access. And difference between register addressing versus register indirect addressing. Register addressing, or that means the value you want to move or want to add is found in the register itself. Whereas register indirect addressing, the value you want can be found in the memory whose address is in the register, right? So you go through R1, like the second case in red. At R1 means you take R1. That's not your operand. That's the address of your operand in iData space. So you take that, whatever value is in R1, you go to the memory address, and then that's where you would get the data, right? You either store there or you fetch from there, okay? And if R1 contains 20 hex, 20 is not necessarily your data, but 20 is the address of your data. And also R2 through R7 cannot be used with the at sign. But this, you you could actually use a stack pointer as another way to do indirect addressing. Stack pointer is set to the on-chip address, and when you do push and pop, that's when you get the and get or put the item on the stack. So here's just a simple illustration. So if you do a move a comma R0, in other words, you move the content from register R0 to A, then if R0 contains 3, then after that A contains 3. But if you move A at R0, then if R0 contains 3, then you go to address 3. And if address 3 is in same as bank 0 R3, then it grabs the 1 from address 3 and then writes it into A. So they do different things. That's one extra direction level of indirection. Okay, so here's a simple example for copying constant to an array. So you could do something like put some constant like 55 hex to A, and then you have move the 40 hex comma A. That is, put the constant 55 hex at address 40 hex, right? And then you can fill basically the locations 40, 41, 42, 43, 44, right? All with value 55 hex. So that's a simple way to do this. And you say, that's not very smart. So another way to do it is to use a loop. When you have to do array access or pointer, then you can set up R0 to be your pointer. In other words, the starting address, which is 40. And then instead of moving to a constant location, you move indirect, right? You do the at R0. So that moves the content of A into the location pointed by R0, right? So it starts from 40 hex, and then you increment R0, and then you move again. That's now 41, and then increment again. And then, so this is the inline version, and then as you can see, you can do a loop, right? So that way you just have to do the move and increment in a loop once. Okay, so you can do DJNZ or something to keep looping. And of course, this one is the loop version, right? So you divide into two parts: the initialization, right? Setting up A to 55, and then setting up the address, and then the count. So as you can see, you start to see the structure of a C program, right? It's like a for loop, right? You have for, the pointer gets the address, the starting address, and then count, right? And then, or like a while loop. That's another way to say, because DJNZ actually maps directly to the do while loop, right? Increment, that's like array plus plus, and the assignment is like star array gets the value, right? So yeah, a lot of times, yeah, you can see how like the high level language might be mapped down, but in assembly there are ways you could probably tweak it and make it work more efficiently. And it's important that you know what your code looks like even when you write the high level language, because sometimes a small little difference can in the high level language can make a big difference in the assembly level. Okay. This is another one which is to clear 16-byte array starting at another address. Overall structure looks very much the same. And then you can do copying. You want to do like star p plus plus, it gets star q plus plus. Everybody knows what that means, right? Right? Yes. Say yes. Right, so that means to dereference the p pointer, right? Assign the address, the byte at address pointed by p to the value pointed by q, and then after the statement you increment both p and q pointers, right? You don't increment the content pointed by p or q. You increment the pointers, right? So they both move down by one position because of the precedence rule, right? You remember? Um, so now, so that single C statement translates down to the assembly code you see. So you initialize, well, actually the initialization is not there, but anyway, so it's first initialized R0, which is your destination, right? And then R1 is your source. So R0 is your P, R1 is your Q, and then you have the counter. And so this illustrates the use of both R0 and R1, right? Because one acts as a source, one acts as a destination. So having R1 and R0, two of them, I think that's actually enough. And so it basically does the now move A and then at R0, and so that's to load the byte from the source, right? And then move at R1 comma A, so that writes it to the destination, and then you increment both pointers, right? And then DJNZ to decrement the count, right? And so as you can see that those couple instructions will accomplish the assignment in the loop. Now, indexed addressing mode is used for uh, basically something like a table lookup. And very often that's done with a code memory. Okay, so what's index addressing? So you have a base address and then some index. Okay, so index is in C, that's the square bracket, and then some index could be 1, 2, 0, or whichever. And in 8051, one of the move C instructions looks like this. The syntax looks like move C A comma at A plus DPTR. What does that mean? That means what you have on the bottom there, if that makes sense to you, right? So A is essentially the index. And then what you do is you have the DPTR as your base address. You don't change DPTR. You keep it the same, but you load the index into A, and then that forms your effective address. Then you use DPTR plus A as your effective address to load from. Where does it put it into? Well, it overwrites A. Right? A was your index to begin with. Now it's overwritten with the content. Right? So that is how 8051 architecture can support some kind of table lookup. Okay, so it's using the A as the index, and after loading, A has the value. Okay, so that's index addressing mode.